Is my slide visible?
Oh, you start this from
Yes, sir.
this class.
Okay, yes. So, welcome
I
everyone
am.
to the week 12 discussion of this course, Computer Vision. And this course is officially taken by Professor Jayanta Mukhopadhyay, Professor Computer Science and Engineering Department, IIT Kharagpur. Myself, I am Paul. I am a PMRF research scholar from IIT Kharagpur, and I am a PMRF TA of this course. By TA, yeah, by TA my responsibilities are I will discuss some of the questions that are very similar to your assignment, so that whenever you will solve the assignment it will be very easy for you. Okay, but before that I always prefer to just briefly discuss whatever has been discussed in the week, and then we will proceed to the question answer session. Okay, so in the previous class what we discussed regarding dimensionality reduction, right? Dimensionality reduction, PCA, etc., right? But this class we will be delving more into this neural network. Okay, so neural network we have introduced this concept neural network in the week 10. Okay, whenever we were talking about classification, in classification only I have told you neural network is one of the ways, or one of the techniques for this classification. Okay, so neural network, the basic of neural network is nothing but your simple perceptron. Okay, and simple perceptron stacked in different layers. So there are definitely three layers. One is known as this input layer, second is this hidden layer, and third is this output layer. Okay, hidden layer can be many, not one but many. Input layer is generally one, output layer is also generally one. Okay, so in between there can be many hidden layers, and all these neurons are connected to each other, so for the flow of information from your input to your output. Okay, and whenever you are talking about, yeah, what are the parameters are nothing but weights and biases. Okay, so what is known as training of the network? Training of the network is nothing but just updating this parameters, that is weight and biases, that we do by back propagation. Okay, so that is the brief about this neural network. Now neural network, that is neural network NN, right? But today we will be discussing something known as CNN, that is convolution neural network. Okay, it is also a type of neural network only, but instead of using our basic neuron we use this convolution layers. Okay, and CNN is basically more used for this image detection or classification, whatever. Okay, so that is CNN. So what is this convolution layer? Convolution is nothing but filter. Okay, this filter or kernel. Okay, that is convolution. So purpose extract features, is just texture, shape, etc., from the input image. That is the purpose. How it works? A small matrix called as filter or kernel convolves over the image. Convolves means slides. Okay, nothing but slide. That means there will be a big image like 28 cross 28 or 18 cross 18, any dimension. Okay, and it is actually a three-dimension image. Why we are calling it a three-dimension image? Not in that dimension, that is depth, but here the dimension, whenever we are talking about convolution layer, here the depth means the number of channels. for example, our RGB image is nothing but it consists of 3 channels. So that is why 3 depth we take as 3. Okay, so that is input, and input is nothing but, input is your image, and that is nothing but, if we talk about dimension of input, that is nothing but your width, that is W, your height, that is H, and your depth, that is number of channels. So that is why like 28, if I have this 28 cross 28 image, so 28 cross 28 cross 3, that is your image dimension or your input dimensions. Okay, but after input we are convoluting it. That means we are just moving a filter over this convolution over this image. Okay, so that is why it is known as convolution operation. Okay, so this filter can also have different shape. Okay, that is known as this kernel size. Okay, kernel size. So filter is nothing but your small matrix. If I talk about image, if that is a 28 cross 28 matrix, your filter can be 3 cross 3, 5 cross 5, 7 cross 7, etc. Okay, so that is the dimension of the filter. Okay, and when input dimension is your image dimension, your filter dimension is your filter dimension, and after this filter convolved over the image, we will get an output dimension that we will discuss. So this is the convolution operation. Okay, so this you can see it properly. So x is nothing but your input image, and then k is nothing but your this kernel filter. Okay, and then this is your output, or the output of the convolution. Okay, so that is known as output feature map. Okay, so that is the whole convolution process. So at each position it performs an element wise multiplication and sums the result, producing a feature map. Different filters learn to detect different features, edges, corners, or patterns. So that is the whole about this convolution layer. For example, this is what I was talking about. Like, this is your image. Okay, 32 cross 32 into 3 because we have this 3 channels, so that is why 32 cross 32 into 3. So that is your image dimension or your input dimension. After that, this is your filter dimension, 5 cross 5 into 3. Basically, if this 3 is also not given, so you have to assume that your depth of filter is nothing but your depth of the input image. So that is why 3. Sometimes it would be written like 5 cross 5 filter or a 3 cross 3 filter, but you have to assume that the depth is equal to the input image. Okay, so that is why this is the filter. After that, this is your output. Okay, so from 32 cross 32 we got this activation map 28 cross 28 into 1. Okay, so that is the that is regarding the output dimension. How we got this 28 cross 28 we will be discussing in the next slide, but this is what you have to do. So this is your input, this is your filter, and this is your output or the activation map. Okay, so that this is the whole thing about this convolution network. So very easy, again I am repeating, this is your image or the input, that is nothing but whatever dimension it has. It has 32 cross 32 dimension, and 3 is your number of channel, because R, G and B. So that is why 3 channels, so that is why 3 is the depth. We have this 5 cross 5 filter. Now 3 can be written, cannot be written, but if 3 is also not written, you have to assume that the depth of the filter is nothing but your depth of your input image. So that is why 5 cross 5 into 3. And after this, putting this filter into this, we got this activation map, that is 28 cross 28 into 1. Okay, why 1? The output dimension is nothing but the number of filters that we are stacking it. So as we are using only one filter here, so that is why 1. Okay, for example, here like we have used 6 convolution, 6 number of filters, so that is why this is the total depth, that is 6. So that is the whole thing about this convolution layer. Okay, now what are the features of convolution layer? So we have this locality, that is object tend to have a local spatial support. Then translation and everything is you can just read the theory, I am not discussing, but this is important, that is weight sharing. So whenever we are talking about this simple neural network, so simple neural network, you can have different weights for different neurons, right? So last in the 10th week you can just check, The numerical I have discussed also. So for example, numerical I have discussed also, that has different weight for different neurons, different weight. But here what is happening, as we are using the same filter and convolving it, that is moving the filter from here to here. Okay, so that is means if the filter has the same weight, so as we are convolving or sliding it, and we are using the same filter, so we are doing the weight sharing. That means we need not have to have different weights. We are, as we are using the same filter again and again, just sliding it, so that is known as weight sharing. So why we are doing weight sharing, why we don't have feature for every image? Because definitely if we are using so many filters for each part of the image, so what will happen, we will have so many dimension, and then we will have this what that is called, that is we will have over predict the thing, or yeah, over predict the thing. Okay, so that we should not want. So that is why we are using this weight sharing, as we are just convolving the same filter again and again. Okay, so that is why we are doing the weight sharing. Okay, and then there is this non-linear layer. So at last we have this or even in between the convolution layers also, we are having this non-linear layer. So we use different type of function like sigmoid or ReLU. Commonly we use this ReLU function. So that is some of the features of this convolution. So this is the most important thing that will definitely be important, or very important for your exam point of view, that is to calculate the output volume of your activation map. Okay, so output volume of your activation map, I have told you this thing, that we have this input dimension, we have this filter dimension. From this we have to get what is the dimension of this activation map. So how to get the dimension of this activation map? So this is the thing, right? If I want to get the W2, that is the width of the activation map, so that is calculated by this formula, W1, that is the width of your input. Okay, and minus FW is nothing but your filter width, and plus 2PW. Yeah, what is this P is known as padding. Now what happens is, whenever we are talking about convolution operation, like this is your 3x3 image, right? This is a 3x3 image. Okay, so if I want to have the 2x2 filter, so how I will project it? How I will project it over here, and then I will project it over here, I will project it over here, and then I will project it over here. So that is how, that is stride equals to 1. That means I am moving, I am first pointing over here, and then I am pointing over here. Okay, so that means I am sliding one by one. Okay, so that is stride equals to 1. So that is the below thing, that is stride. And we have something called padding, that is PW. Why padding is used? Padding is used because whenever we are just fitting this filter, so we are ignoring the we are ignoring the whatever this edge. Okay, edge, we are ignoring it because our main thing will be over here. Okay, so that is why we are ignoring the edge. To not ignore the edge, we have this padding. Okay, what is padding? Padding is nothing but a zero layer added over here, over here, over here, or over here. So that is known as padding. So this PW is nothing for this padding. So width of the input layer minus FW, that is width of the filter, plus 2 into padding. We generally use zero padding. Zero padding means nothing but 0, 0, 0 written over here. So that is padding. So 2 into 0 padding divided by SW. SW is nothing but a stride. That means how we are shifting. For example, we have this 5x5 image. So 5x5, we are using 2x2 filter. So first we will be pointing filter over here. Okay, and then what we will do, if we will have one stride equals to 1, then we will put filter over here. But if we have this 2 stride, then what we will do, first we will point filter here, and then we will point filter here. That means no overlapping. So that is 2 stride. Similarly, we can have more than 2 stride also. That is stride. So similarly for the height dimension, that is the vertical dimension. So that is h2 equals to h1 is nothing but input height minus fh, that is the filter height, plus 2 into padding and divided by sh is nothing but your this stride in the horizontal in the horizontal, or you can say in the okay, width is at h2, it is written by h2, so h dimension, that is vertical dimension, and plus 1 you have to add. So by that you will get this thing, that is the dimension of your activation map. Okay, so here this dimension of your activation map here, by this you can calculate. And last we have this d2 equals to d1, that means the dimension of the filter, that will be equal to dimension of your input image. Okay, but if you are using so many activation so many filters, so your total depth will be nothing but your number of your input number of your filters. Okay, so that is the whole thing regarding the dimension of the output. And then we have this, how many number of parameters we got. So parameters, that will be calculated by this, that is fw into fh, that is nothing but your dimension of your kernel or the filter, into d1 is nothing but your d1 is nothing but your this input dimension or the number of channels, if I say in a layman term, into k weights, that is the number of filters you are applying, into k biases, that is number of same thing, k is nothing but your number of filters. So by this you can do all your calculations. So this is the most important formula that you have regarding your convolution operation. Okay, so any doubt in this? Clear, right? W2 equals to W1 minus Fw plus 2Pw divided by Sw plus 1. Similarly, you can calculate for H2, and then you can see the this depth. Okay, depth is nothing but your depth of your input image only. But if you are using so many activation layers, so that will be n into, that is number of filters, into your this dimension. Okay, so that is the whole thing regarding this convolution neural network output. Okay, so this is the thing. Now our next thing is regarding this pooling layer. After this convolution layer, in the CNN we have this pooling layer. So what is this pooling layer? Pooling is nothing but to progressive reduce the spatial size of the representation. So this is your total size. Now after pooling layer, what we can do, we can easily reduce the spatial size of your layers. So that is pooling. So what is this pooling? Generally we use this two technique, that is maximum pooling and average pooling. Okay, so what is pooling? Like you can easily see in this diagram. So this is after your activation map. After you got your activation map. So for example, this you got your activation map. Now you are using 2x2 pooling. So what you have to do? You have to now what you have to do? You have to do the 2x2 pooling. That means you have to just put the pooling filter here. So pooling filter here, and then pooling filter here and here. Similarly, just like your stride and everything. So this is how you have to do it. So what is average pooling or maximum pooling? For example, this thing 2x2, I have to do the pooling. So how I will do the pooling? It is very easy. So just it is very easy. See, 1 plus 1 plus 5 plus 6 divided by 4. So that is average pooling. So that is 2 plus 5, that is 7. 7 plus 6 is 13. 13 divided by 4 is what? The 13 divided 3 point something, right? 3.25, I think. So this is your average pooling. And now what will be the maximum pooling that has been done in this example? That is nothing but the maximum value that you got from this. So 1, 1, 5, 6. What is the maximum? Maximum is 6. So that is why if I do maximum pooling, it is 6. Similarly, if I do this green color maximum pooling, it will be 8. This yellow color maximum pooling, 3. This blue color maximum pooling, 4. So by that you are doing the pooling operation. Okay, so example also here also it has been given. So maximum pooling 1, 3, 2, 4, it is nothing but 4 will be your maximum pooling. So pooling is nothing but we are reducing the spatial size of the activation map that we are got from this convolution layer. okay, or convolution operation. So that is pooling. Again, same thing, output, if you want to calculate the output, that will be calculated by this formula. Generally here we do not use padding. Earlier in this formula we have this padding, that is 2p added, okay. So but here we do not use padding in pooling layer, so that is why we just remove the p and everything remains the same, okay. Everything will remain the same. So by this you can get the output volume after this pooling operation. Now what about parameters? Now pooling does not have any parameters, that you have to always remember, okay. Pooling means no parameter. Earlier for convolution, this is the number of parameter for your convolution, but pooling has no parameters, because the weights pooling has no parameter, because here no weight is given, right. Like convolution, you are giving this weight, that means in this filter you have some values written in it, right. But here there is no such values written in it, okay. So that is why it has no parameters in this pooling operation, so that you have to again remember. So this is regarding your convolution and pooling. The formula will remain the same, just here as we do not use this zero padding. Why we will use zero padding? For example, if you want to do maximum pooling, so 0 plus something, that will give us nothing. And then average pooling also, if you will do, it will only reduce our values, okay. So that is why we do not use zero padding here. So that is why just remove the p and other things remain the same. And parameters for here, or parameter will always be 0. So that is regarding the convolution operation and the pooling operation. At last we have this fully connected layer, okay. So purpose, make the final decision, whatever, like in classification you have to do the classification, in regression you have to do regression, so anything, okay. And how it works, flatten the feature map into a 1D vector. So the last convolution filter map that you got, what you have to do, you have to flatten it into a 1D vector. That is nothing like you got like 32 into 32 cross 3, right. So flatten means you have to just do the multiplication, 32 into 32 into 3 into a 1D vector. So that each neuron is then connected to every neuron in the next layer like a traditional neural network that we have already discussed. Learn to map high level feature, class, course, docket, etc. Okay, so that is how this is the fully connected layer. So this is the whole flow of the CNN flow. That is very important, that if you remember this, your concept will be very clear, okay. Yeah, so this is the whole flow. So convolution layer, extract features, pooling layer, that is reduce the dimension, keep strong features only, and then repeat convolution plus pooling, and at last we have this fully connected layer. Use extracted feature to classify the image, or do the final, or take the final decision, or give us the final output. So that is regarding the whole CNN flow. If you just keep this in mind, your process will be very clear. So this is the CNN flow. So this is the analogy convolution layer. This is just feature detector, eye for scanning shapes. Pooling layer summarizes, keeping the most important parts, and last fully connected layer, this is the decision maker or the final convolution. So this is regarding the whole convolution layer or CNN. So again I am repeating, we have these three things. One is this convolution layer, second we have this pooling layer, and third we have this fully connected layer. We can have the series of convolution plus pooling layers, and then we will have, at last we will have this fully connected layers. Convolution layer, that extract the features. Pooling layer, it reduce the dimension and keep only the strong feature. Fully connected layer, it takes the decision. Okay, so that is the whole CNN flow. And then we will have this two things. One is this batch normalization, and then we have this dropout. Dropout. Okay, so batch normalization. So again, this is the core concept of neural networks. So batch normalization. So at each hidden layer, what happens is whenever we are putting this activation function, so our this distribution, for example, if you earlier have one type of distribution, whenever you are applying this activation function in each hidden layer, what happens is your distribution will get affected or changed. So to avoid this, we have this batch normalization. So batch normalization, how we do it? We first compute the mean and variance So that is how we do, and then we do for each pixel we do this normalization, and then shifting we do by this yi gamma xi plus beta. But you have to keep in mind this gamma and beta are learnable parameters. Okay, so this is not random parameters, but this again we learn from the neural networks. So that is the concept of batch normalization. What benefits we have? It stabilizes the gradient. So back propagation during training means back propagation, and back propagation it always deals with this gradient. Okay, someone is joining. Yeah. So it stabilizes the gradient, allow a higher learning rate, acts as a regularizer, make network less sensitive to weight initialization. That is very important, because neural network we already do weight initialization. So weight initialization it does a strong factor in our result. Okay, so what it does is it makes the network less sensitive to weight initialization. So these are the some of the things regarding batch normalization. We have this second technique known as this dropout. So dropout, as we will have in this long networks, what happens is we will have so many neurons and connected to each other. So if we have this so many neurons, so we have this problem of overbias. So to deal with this we have this overbias or overfitting. So to deal with this we have this dropout. Okay, so dropout it prevents overfitting by forcing the network to not rely on specific neurons. So during training we randomly drop a fraction of neurons with probability p. That means we do not take all the neurons, we intentionally drop some neurons with the probability p. So that is dropout. Implementation, this is how we implement it, like just we choose a probability or by which we should drop the neurons, and then we drop the neurons like that. Typically 0.5 at 1 at hidden layers and 0.8 to 1 in the visible layers, that we do the dropouts. Inference testing, no neurons are dropped, weights are scaled appropriately, so expected output remains the same. So these are all theory, so I am not going in detail, but summary is important. So just batch normalization normalizes activations per mini batch, making training faster and more stable, and then we have this dropout, randomly drops neuron during training to prevent this overfitting or overbias, what overfitting. So this is the entire thing regarding this. This is the entire thing regarding this neural network or the CNN. Okay, and then we have this different CNN architecture. Any doubt regarding this CNN? At least you got the flow, that is important. You understand what is a convolution layer, you understand what is a pooling layer, and then we have this fully connected layer, and then we have this different techniques in between like batch normalization, dropout, etc. To have different thing that we required. Okay, so that is the whole thing regarding this CNN. Okay, so any doubt regarding this? What is important? Important is if I talk about quotients point of view, then the most important thing is to calculate the dimension of the activation map, either after the convolution layer or the pooling layer, and also the number of parameters. So that is the most important thing regarding your quotient answer part. Okay,
Sir, I have one doubt in pooling layer.
pooling layer, yes.
Yes, can you go to the slide?
Yes.
Uh, you put the formula for W2 and H2
Yeah.
in denominator S or SW, sir.
Yeah. Stride, that is
You
stride.
put uh,
Yeah.
SW or SH, sir. For
As
the calculation of W2, you
yeah, it
put
is,
S.
yeah, SW and SH same thing. Okay, SW SH is stride is given over here, right? So it will be
Okay,
SW
okay, okay.
SW here and SH here, but the same thing. Generally stride we use the same in the width also, and height also we use the same. That is why S is only written over here. Okay, so
Okay,
generally
okay.
when we talk about 2 cross 2 filter, so generally we use the stride divided by 2. Okay, so that is the thing. For example, here you can see what we are doing, we are just using the stride equals to 2 over here. Okay, so that is the whole thing. So this is regarding this pooling layer. So after that there are some different CNN architectures. So this is again, this is the pure theoretical part, so I will suggest you to read more and more regarding this. So we have this different CNN architecture. So first the LeNet has been introduced. So this is the architecture. First we have this input, and it was used for example for this document recognition. Okay, so this is a letter written over here. So this is the input image and input. Then we have this convolution, first convolution layer, then we have this pooling layer. Someone is joining, yeah. Convolution layer again, and then pooling layer, and then at last we have this two fully connected layer, and then we have this output. So this is the whole architecture. Number of parameter here, that is 60k, 60,000 parameter, and this is the floating operation per inference. Floating operation is nothing but in your neural network what happens, that is that if I say, that is nothing but your there is a function involved, that is fh, right? F into z, let's say f into z, okay, and z is nothing but that is weight into input, like w into x plus plus the bias, okay. So that is the whole thing. So floating operation means for each if I say this is the z, and f is nothing but your activation function, and if I do the activation function in it, so we get the output. So w into x plus b is nothing but your this z, and if I just do the activation function for this z, we get the output. Okay, so that is for one neuron. Okay, so that we have to do for all the neurons. So floating point operation is nothing but in this operation we have this two floating point. Okay, one we have this this operation that is going on, and then we have this activation operation. So that is why for each operation we have this two floating point here. So here, so in total how many floating point operation per inference? So we have this 341k floating point operation per inference. Okay, and then sigmoid used for non-linearity. So the activation function here, it is used as sigmoid. Okay, so this is the whole thing regarding LeNet, and then we have this AlexNet. Again you can read it, like this is the total architecture. Here we have more number of network, more number of convolution layer and pooling layers that you can easily see, and then we have this three fully connected layer. LeNet we have this two fully connected layer, but here we have this three fully connected layer. Okay, and then we have this ZFNet. It is AlexNet, but again the filter size has been changed from 11 to 11 and stride 4 to 7 to 7 into stride 2. Okay, so that is how Alex, it is similar, the architecture is very similar to AlexNet for ZFNet, but only the filter size has been changed, and by this they have reduced the error from 16.4% to 11.7%. And then we have this VGG has a different type of layer. For example, there is VGG 8, that is only 8 layer. Then VGG 13, sorry, VGG 13 with 13 layers, VGG 16 with 16 layer, and also VGG 19. So different type of architecture. So here also here also there are different filters and stride that has been used. So again you can just read the theory over here. Then we have this GoogleNet and ResNet, that are very important. So GoogleNet, it introduced this inception module. So what is this inception module? Inception module concatenates output of filters of different sizes. Okay, so that is the important thing about GoogleNet. It introduced this inception module. So inception module, it does whatever the feature map it has got from different type of filter, it concatenates it. Okay, so by that it introduced a new type of thing in this neural CNN architecture. Okay, so that is GoogleNet. So GoogleNet, it reduces the error to 6.7%. And then at last we have this ResNet. So ResNet, what it does is it has this residual mapping. So what it does is that if we have so many layers, okay, so many layers, so what happens is if I talk about the input, if I talk about the output, till going to output we generally miss some of our information of input. So That is why it introduced this concept. So this, what it does, it takes the output of the previous layer, but it takes the output of the previous to previous layers also. So this is the added thing. Okay, this is the added thing over here. So this is the you can say innovation of this ResNet. Okay, so ResNet, it has more depth like 152. You can have up to 101, 152 layers. So this is the whole CNN architecture. So this is the whole summary I have given you. So you can just easily read it, like what year this things are introduced. LeNet has been introduced in 1998, then AlexNet 2012, ZFNet 2013, VGG 1619 that is 2014, and GoogleNet 2014, and ResNet, this is the recent one, that is, it has been developed in this 2015, and these are the number of layers. You can easily see ResNet has the more number of layer. Key features also I have given. Dataset, what dataset has been used to train these models, and then at last what are the limitation of this. So this is the evolution trend also I have given. So first from LeNet to AlexNet, then AlexNet to ZFNet, LeNet to AlexNet, from shallow digital recognition to large scale image classification, then AlexNet to ZFNet, improved hyperparameters plus visualization, ZFNet to VGG, deeper and simpler design using only small filters, so that is important, ZFNet to VGG, and then VGG to GoogleNet, depth plus efficiency using this inception module, that is important in the GoogleNet. And ResNet solved the vanishing gradient problem using ultra deep network. Okay, by this this thing. Okay, this is very important. This is the innovation of the ResNet. So this is the whole story of your different CNN architecture and what are the evolution trend. So all this theory, I request you to just after this class you can read all this theory whatever has been in the slides. Okay, so this is regarding this. After that we have this what are the training tips and etc. So again I am telling this in brief. So we have this two step. One is this training step, and second we have this data augmentation. Okay, so training step, pre-processing step and data augmentation. So whenever you got any image data, first you have to pre-process it. For example, you have to normalize its size, etc., and then you have to do the data augmentation. So what is data augmentation? So whenever we are training all this network, we require more number of images. More number of images whenever you will use, then only you can generalize the network. Otherwise, if you are training for only a very small number of image, what will happen is whenever your you will get a different test set to your trained model, it will not give you the right result. So for that you require more number of image, but more number of image you cannot just click the images again and again, right? So what we do, we take a few number of image and then we put this data augmentation technique. So from less number of image, we multiply the number of image by different type of augmentation, like horizontal flip, and then random crops, then distortion, transformation, etc. By this what we do, we create from less number of image to more number of images. So these are the two training steps first you have to do in this dataset preparation. Okay, and then what we do, we generally use this transfer learning. So what is this transfer learning? That is very important, and anything that today you will do, you will take the help of this transfer learning. What is this transfer learning? Transfer learning means already a model has been trained. Okay, now you do not have to train each layer of the model, but only training a few layer of the model, you can custom train your model. So that is transfer learning. For example, if I have a model that has been trained for classifying 20 different type of images, okay, that has been already I have. Now again from scratch, I do not require to train all the layers of the model. Rather what I will do, I will take this pre-trained weight and then I will train this I will train this model according to my few images. Okay, whatever I want, according to that I will train this. So by doing this, what I am doing, I am not training all the layers of the model, but I am training few layers of the model. The the layers in the bottom, these are already trained. So that is why we freeze this training over here, and we only train for few of the layers. Okay, so that is known as transfer learning. So already we have this pre-trained model. So any thing that you will do today, so we are all have all this pre-trained model available to us. Now what we will do, we will just take the pre-trained model, and then we will supply our images, and we will train few layers, not all the layers, but we will train few layers. By this we can complete our training very fast, and we can build our model very quickly. So that is transfer learning. So application, that is very vast application. One is this classification, then we have this recognition and localization, or commonly called as detection, then segmentation and image captioning. So these are different applications. So again, I hope this all things are clear. What is this classification, detection, segmentation and captioning? So classification means you will just give a image like different fruits. Okay, so you will just give a image, you will say what fruit that you have. So your answer, the answer that your model will give, like banana, apple, etc. So that is classification. It will only give you what are the fruits in it. So that is image classification. And then we have this detection. Okay, second is nothing but detection, recognition, or commonly called as detection. Detection, what is that? It does in the image, it will not only give you banana, but it will also tell you where exactly, which position the banana is. Okay, so that is detection. And then there is segmentation is pixel level detection. So detection means this object recognition or detection means it only detect the image by a bounding box, but here bounding box will also be there, but your pixel level segmentation will be there. For example, this is the banana, so your the segmentation will be done for this part. Okay, so that is segmentation. And then there is image captioning is the, you can say, this is the advanced thing. So for image captioning, you also require this RNN or vision transformer, etc. So this is, I kept this separate. So this are the three key things that are used in the computer vision in today's date. One is classification, second is this detection, and third is this segmentation can also be of different types. So one is this semantic segmentation that we will learn. For example, you have to segment all the canopies or all the trees in the forest. So for that you will do a semantic segmentation. But there is another thing, that is advanced level of semantic segmentation, is instance segmentation. Instance segmentation means for example, in the same image you require the where the exactly the banana is, where exactly is the apple is. Semantic segmentation, it will segment all the fruits at once, but here what it will do, it will segment banana in different color, it will segment apple in different color. So that is instance segmentation. Okay, so these are the different thing about computer vision techniques that you should know, whatever the terminology you should know, because these are the things that has been used in research these days. So you should know at least the what are the terminologies. Okay, so this is the whole thing. So I hope this is clear. What is classification, what is detection, what is segmentation? Any doubt in this? And what is this transfer learning? Any doubt in this? At least the concept. Am I audible? Yeah, clear, right? Okay. So after this, this is an exercise question. This is the first exercise question. So consider a deep CNN architecture which takes an image of size this 240 cross 3 as input for the purpose of classification into two classes. 3 convolution layer with filter size 7 cross 7, 5 cross 5, 3 cross 3 respectively. The ordering of the layers starts from the input. The number of channel in this layers are 64, 32 and 60 respectively. 2 max pool layers of filter size 2 cross 2 with stride 2 in both the direction between the first and the second and the third convolution layer. And at last we have this 2 fully connected layers having the number of neurons 50 and 20 respectively. The activation function of each neuron used in the network is the ReLU, that is rectified linear unit function. Answer the following question. Option A, provide a schematic diagram of the architecture of the network. Option B is provide the sizes of the output from each convolution layer. Option C, compute the number of parameters that you require to learn in each layer. So this is the whole question. If you can answer this question, all your convolution CNN question is cleared. Okay, so CNN concepts are cleared. So what has been told, it is a CNN architecture. So we have to create a CNN architecture, because first this, you have to schematic draw it. Okay, so schematic draw it means you do not require to draw everything, just you can draw it by your block diagrams. Okay, so how many convolution layer you have? You have 3 convolution layer. First is this 7 cross 7 7 cross 7 filter layer, and then you have this 5 cross 5 filter layer, and then you have this 3 cross 3 filter layer, this 3 cross 3 filter layer. So you have this 3 convolution layer, and for each convolution layer also the number of channels are given. That is, for 7 cross 7 you have this 64, for this 5 cross 5 you have this 32, and this 3 cross 3 you have this 16. So that is also given. So you can say that dimension of each convolution layer has been given. And then what has been given, the input dimension is also given, that is 240 cross 240 cross 3. And then for this 2 max pool layer where we have to fit between 1 and 3rd convolution layer, 1 and 2nd convolution layer, and 2nd and 3rd convolution layer. And the max pool layer has this 2 cross 2 max pooling layer. Okay, so that is the thing, 2 cross 2 over here also, and 2 cross 2 over here also. And then we have this 2 fully connected layer, one with 50 neurons and second with 20 neurons. So this is the whole architecture. So this is option A is clear. Now option B, provide the sizes of the output from each convolution layer. So very easy how you can do it. This is your input layer, and then you have to apply this formula. Okay, so the formula, that is very easy. This is the formula I have told you. So W, this is the formula that I have told you. This formula you have to apply, W1 minus FW plus 2PW divided by S. That you have to apply again and again. So this you have to apply. So just apply this. So whenever you will apply this, you can get all your dimensions. So so by this you can get all your dimensions. So you can just apply, as there is no pooling layer, we have only there is no pooling, not pooling, there is no padding. So there is no nothing mentioned about padding, right? So padding, you can just ignore this P, and just you can write W1 minus whatever your W K is there, and then you can solve it. Like 240 minus 7 and plus 1 you have to add it. Actually the formula is the W minus F divided by S, W minus F plus 2P divided by S plus 1. So S, whenever we are talking about convolution layer, there is no stride, or stride is 1 only. So that is why the denominator can cancel. So what will be, it will be 240 minus 240 minus 7 divided by, no pooling is there, divided by 1, because 1 is the stride, and plus 1. By that you can calculate your dimension. So your answer will come 234. Similarly you can do it for the width also, so the height also. So this I have calculated for width, and similarly you can calculate for the height also. Same thing will come, because all the dimension are for the width and height are same. And then into 64, that is number of channels are there. So number of channels, that will be 64. So by this you can easily get your dimension of output from each convolution. Okay, and then after this, how you can get your dimension for max pooling? Very easy. Dimension for max pooling, what you have to do, as there is no convolution, so this thing will be 0, and divided by stride is 2, because stride is 2 has been given, so divided by 2. So how you can do it? 234 minus 0 divided by 2, that is 117. So 117 into 117, and number of channel will remain the same. And after that you have to do for this, so very easy, again 117 minus 5 plus 1 divided by 1 plus 1, that will be give you 113, and similarly you can calculate all the dimensions. At last you have this thing that is very important, that is what is the dimension of the fully connected layer. So dimension of fully connected layer, whenever we are talking about fully connected layer, so I have told you have to flatten the layer. So whatever answer you got from the last thing that that has been here, what you have to do, you have to flatten the layer. So flatten the layer, that is why you have to just multiply it. So that will be 54 into 54 into 16. So here you are getting 56 into 56 into 32, and you have to do this convolution. So 56 minus 3 divided by 1 plus 1, that is 54. You will get 54 into 54 into 16. So that will be your fully connected layer. And at last, what is the number of parameters? So number of parameter, again there is a formula for number of parameters, so that you have to remember. So that is what, that is nothing but your this dimension, the filter dimension into your depth into this into number of channels, that is 64, plus 64 is the bias. So by that you can get number of parameter from first convolution, and then similarly you can get number of convolution from second convolution and third convolution. And here also you can get the number of dimension for the fully connected layer, that is this here also you can get by the same thing. And at last for this fully connected layer with 20 also you can just do the same number of things. So that is how you can solve the whole question. So any doubt regarding this? Any portion you have any doubt? I hope this is clear, because this question will not the whole question, but a part will definitely come in your exam or any assignment. Okay, because that is very very important question. So by that, let's move further. So this is the object recognition and localization. So classification we have already discussed in the week 10, and now we will be talking about detection and segmentation. So object detection, recognition and localization is nothing but your detection. So detection, this is what I was telling. So detection means like dog, not only if this is a classification, so you will get only dog, person, car. Okay, no detection, but in detection there will be bounding box also, means where exactly the dog is located in the image. So that is known as object detection. Okay, it is also here in this course, it has been called recognition and localization, but actually it is commonly known as detection. So this is the detection. Detection means like where exactly the person is, where exactly in the image the horse is, where exactly in the image the car is. If it is a classification problem, then your answer will be car, comma, dog, comma, horse, comma, person, comma, person. That will be your classification answer. But if it is a detection, then you have to give all these classes also, and also where exactly the classes are in the images. So that is detection or localization, it has been said over here. Now these are the different again different models are there for this detection. So these are a two-stage detection model. So detection model also today what we are using, today we are using mostly this single stage detection model. Okay, so the detection model that has been used in this course are actually the double stage detection model or the two-stage detection model. Okay, so the two-stage detection model, these are the common detection model that has been used in this course. One is RCNN, Fast RCNN, and Faster RCNN. Okay, again you can just read the theory, I am not going into details. So again you can just see the theory. For your question point of view, if the question will come from RCNN inference, then this is the total time that is required for inference in your RCNN inference. Okay, inference means for getting the result. For example, after you trained your model, your actual task is giving an unknown data to your model and get the result. So for getting the result, how much time is required, that is known as this inference time. So this inference time can be told for you to calculate. So inference time for this RCNN model, this is the total inference time, that is the proposal time, prop time, time taken for generating all the proposals, and then number of proposals into convolution time, and then number of proposal into your FC time. Okay, time taken to identify the object in the image. Total when we will do it, that is proposal time plus number of proposal into convolution time and number of proposal into your this time taken to identify the object in the image. That will give you the total inference time for your this RCN, and that is important for your quotient point of view. Again, another thing that is important for your quotient point of view, this is regarding the inference time for your fast RCNN. Okay, so this is only RCNN, but now we are talking about fast RCNN. Fast RCNN or faster RCNN, the formula will remain the same, and this is your formula, prop time plus, here it is 1 into convolution time, here it is number of proposal into convolution time, but your fast RCNN, it decreases the convolution time by this, that is here it is 1 into convolution time, but here it is number of proposal into convolution time. So that is why the time get reduced. So that is why this is known as fast RCNN from your RCNN. The detail you can just read from your text. And then we have this so called faster RCNN, again you can see in text. So this is the overall summary. So we have this RCNN that is introduced in 2014, fast RCNN in 2015, and faster RCNN again in 2015. So RCNN, it is the reason based CNN, that is the full form RCNN, that is reason based CNN. CNN is nothing but convolution neural network. So it has been introduced in the year 2014, and reason proposal, it uses a selective search. Okay, faster RCNN also, it uses a selective search, but whenever we are talking about faster RCNN, then it uses this reason proposal network or RPN, that replaces the selective search algorithm. Okay, so that is the you can say evolution from your RCNN to faster RCNN. And regarding feature extraction, so this is about reason proposal. Okay, and then second thing is feature extraction. So feature extraction, RCNN, we use this CNN AlexNet that runs separately on each reason. Then this for this fast RCNN, we have the CNN feature map computed once per image. Okay, so that is why faster RCNN. So that is why also you can understood in this inference time also, we are we are talking about number of proposal into your time, and one we are using 1 into convolution time. So this is the modification. So CNN feature map computed once per image. Okay, so that is why this time gets reduced. Reason extracting using ROI pooling. ROI is reason of interest pooling. And then we have this feature extraction here, CNN feature map, both RPN and RPN, that is reason proposal network, and ROI pooling. And classification, first we are using SVM classification, then softmax, and then at last also we are using softmax. Speed, if I say, so earlier it was 47 seconds per image on GPU, faster RCNN only 2 seconds per image, and fast RCNN 2 seconds per image, and faster RCNN it gets again reduced to 10 times, that is 0.2 second per image. Okay, so that is the whole evolution. And again evolution trend also I have given. RCNN good accuracy, but problem is it was very slow. And then we have this faster RCNN shared feature map plus all this thing, you can read it. And then we have this faster RCNN. RPN, reason proposal network, the backbone of this faster RCNN enable near end-to-end training. So this all thing you can just read it, so nothing to explain. And then we have this semantic segmentation. So I have told you classification we have read in week 10. Then last slides we have discussed, these are regarding the detection. and then we will move on to this segmentation, that is pixel wise detection. Not only detection, but here it also get the shape of the image, because we are doing pixel level detection, so we can also get the shape of the image. For example, in detection, like banana over here is there, so you cannot get the you cannot get the you cannot get this shape, okay. But here in semantic segmentation or segmentation in general, you can get the shape, because this bounding box it will generate, but also it will give you this segmentation or pixel wise detection, okay. So label each pixel in the image with the category level. Don't differentiate instances, so this is semantic, so it don't differentiate instances. For example, two banana are there, it will segment it in a single thing, because banana is only there. So that is why it don't differentiate instances. But if you will move from semantic segmentation to something called as instance segmentation, so what you will also get the number of instances. For example, two banana are there, so it will segment one banana and then it will segment another banana. So that is the instance segmentation, okay. And then even instance level segmentation, it even differentiate the instances. So these are the thing, and we have this something called as upsampling or max unpooling. So previously we have talked about pooling, now we will be talking about this max unpooling. Okay, max unpooling, it is very simple. For example, this is your original image. After that you have done this max pooling. So max pooling 2 cross 2, so this is the 5, this is the 6, this is the max. For example, this, okay. So just this is the 5 is the maximum, here 6 is the maximum, and here 7 is the maximum, here 8 is the maximum. So this is max pooling. Now what you have to do, you have to do the upsampling. So previously we are doing the downsampling, that is we are reducing the size or a spatial orientation, but now you have to do the upsampling. So upsampling, how you can do, so you have this sampled image, and then you have this pooling indices, and wherever the pooling indices are there, you have to just put your this max pooling things. For example, ABCD is your max pooling result. So in this pooling, here you have to give the max pooling, that is A. Here you have to give the max pooling, that is B. Here you have to give the max pooling, that is C. And here you have to give the max pooling, that is D. So that is max unpooling. So previously we are downsampling it, now we are upsampling it. So that is upsampling, that is max pooling. There is also known as upsampling, that is upconvolution. So upconvolution, what is difference between upconvolution? Upconvolution, you are also learning the parameters, okay. So that is the only difference between max pooling and upconvolution. So here it is learned strategy to upsample it, not just this strategy, but there is a learned strategy. So output contains copies of filter weight by inputs summing where it overlaps the output. So that I will just discuss with the question in the question answer session, so that will be much clear. So again, these are the theories. So again, this is the thing that I have told you, like this is exercise 2, given the following pooling indices, maximum unpooled 2 cross 2, the input block X as given below. So this is the pooling index, and this is your max pooling results. Now you have to get the max unpool you have to get. This is the max pooling result you got, and max pooling result that is has been given, and pooling indices has been given. Now you have to do this max unpool. Very easy. 2 you have to put over here, then 6 you have to put over here, 30 you have to put over here, and 45 you have to put over here. So that is how you do the max unpooling. Now there is this up convolution that I will be discussing in the next thing. Then the semantic segmentation, everything is there. Unet already architecture has been discussed, so you can just read the theory. I am not going into detail over here. And then this is the last portion, that is recurrent neural network. Okay, so we have learned regarding ANN or artificial neural network, that is nothing but this neural network. And then we have learned about CNN. Now we will be learning about CNN, that is convolution neural network. Now we will learn about this RNN, that is recurrent neural network. So I have told you regarding ANN, that is artificial neural network. Generally, it is a feed forward neural network. That is, the information always go in a forward direction, and error is propagated in a backward direction by back propagation. Okay, that is regarding the ANN, or the artificial neural network. Now we will be discussing about this recurrent neural network, that is RNN. Okay, so RNN, that is recurrent neural network. So recurrent neural network means it is only not, the information is only not moving in a forward direction, but it can also move in a backward direction also. Okay, so if I remove this arrow, so the information is only moving in forward direction, so that is nothing but your simple RNN. But here what has been happen, after this hidden layer, what happens is, before going to the output, the information is again passing before the hidden layer. So that is known as recurrent neural network. That means not in a forward direction, but it also takes the feedback. So you can just read in the theory, conventional neural network, that is not CNN, but this is ANN. Okay, and that is not conventional neural network, not convolution neural network, convention neural network they are talking about. So that is simple ANN. So that is feed forward, no feedback. Feed forward, that is very important. But RNN, we have feedback from the output of the neuron. So that is very important. Second thing is the disadvantage of your ANN, or the convention neural network, that is fixed size input and output. That means if we are talking about this image, so as image is a fixed size, so definitely we can just do the ANN or CNN, and we can get the result. But if we are talking about detection in a video, in detection of a video or speech or anything, the input size is not fixed, right? So as the input size is not fixed, you have to move from your NN to your this recurrent neural network. So sequences in input, the output, or in most general case both. Okay, so sequence RNN can take the sequence, not only single input, but RNN can take the sequence. So that is why RNN is used in video processing or speech recognition, because there the input is not fixed. So that is another thing. And then we have this fixed number of layers in the convolution neural network, equivalent to unfolded feed forward network of infinite number of layers. Infinite number of layers, because we have this feedback again and again coming, and also we have this sequence of input. So that is why infinite number of layers can have in your recurrent neural network. So in short, if I say recurrent neural network is the big brother, or the evoluted part of your this artificial neural network or conventional neural network. Okay, so this is the whole theory behind it. So this is the unrolling of neural network. So here also we are talking about this how we train the network. Here also we are using the back propagation also, only, but here we are using this back propagation over time, because the input that we are getting, that is related to time, because input is not a fixed input, but input that we are receiving, that change over time. So that is why here the algorithm is not back propagation, but it is back propagation through times, that is BPPT. Not only BP, that is back propagation, but back propagation through time. So that is the difference between your artificial neural network and this RNN, or recurrent neural network. Okay, so this is the mathematical part of it. Earlier, to get the output of any neuron, we apply this formula, that is YT is nothing but weight into your hidden layer or input layer. So by this we can get, and if there is some bias, that is a different thing. So this is the formula that we generally use for your artificial neural network. But here what is happening is we have this information not moving in forward direction, but also moving in backward direction also. So that is why to get the hidden information of the new state, this will be the formula to get your HT. Okay, that is the hidden input. Okay, so hidden input, you cannot just calculate by a simple formula, but hidden input you have to calculate by this formula, because hidden input also get influenced by your previous hidden input. For example, ht, that is new state value, that will be given by fw is nothing but the weight associated with, so that is not fw is I think function, okay. And then ht minus 1, that is the old state, so that is important because it also get the feedback, okay. So that is why ht minus 1, so previous hidden input whatever it got, so that also it takes into account, and xt, that is the original input, okay. So that is the whole thing. So this is the total formula. So ht is nothing but fw, ht minus 1 xt, and ht can be calculated by this, that is tan h, because if you are using this activation function as tan h, so that is how you can calculate your ht, okay. So that is wh into ht minus 1 and wxh into ht. Wxh into ht, that is nothing but this portion is very equal to your previous neural network, but here we are taking the input from the previous hidden state also. So this is new, okay. This is new in RNN. This is new in RNN. This we already have in our artificial neural network, but this is new in RNN. So by this we get the hidden state, and then same formula to get the output. So that is the difference between your recurrent neural network and the artificial neural network. So again we have this different type of application. You can read like this is the difference between your CNN and RNN. I have given all the things, so you can just read it after the class. You can just read it how we can use it, and at last we have this different type of recurrent neural network. So this is the one-to-one, so that we generally do not use, but we use all this like one-to-many, many-to-one, many-to-many, and many-to-many. So example also you can just check over here. So for this first, that is used in standard mode for processing without RNN from a fixed size input. So as this is a fixed size input, so this get fixed, okay. So again I am telling, this red layer is input, this green layer is hidden layer, this blue layer is output, okay. So one-to-one, that means one hidden layer and one input layer and one output layer. So that is why standard mode of pre-processing without RNN, that is fixed number of inputs. So this can be treated as your simple CNN, okay. Then after this that is can be used in image classification. Then sequence output. Sequence output means output is many, but you have one input, so that is why one-to-many. So here it has been used for this image captioning, takes an image and image and output a sentence of word. So it is used in image captioning. That means it will take a single image over here, but it will give you a sequence of the words in the output. So that is why one-to-many. And then sequence inputs, for example, examples sentiment analysis, where a given sentence is classified as expressing positive or negative sentiment. So here as sentence is given to your input, so that is why many-to-one, and only you will get classify whether it is a positive sentiment or a negative sentiment. So that is why many-to-one. Then you can have many-to-many, for example machine translation, and RNN reads a sentence in English and then output a sentence in French. So that is language translation, that can be used for many-to-many, okay. And then then at last we have this another type, many-to-many, synced sequence input and output. For example video classification, where we wish to label each frame of the video. So that is why each frame of the video should be labeled. So that is why input is nothing but your, what is a video? Video is a collection of the image or the sequence of image over the time, that is video. So sequence of image, all the red will take each frame of the video. So that is why sequence of image and combining it is a video, and output will also be in combined form. That result will also be in combined form in the video form, and each blue box will give you your video classification, okay. So that is the different type of networks. And again some examples are given, you can just check over here. So this is regarding the whole thing over this class. So what we have learned regarding convolution neural network, then different CNN architecture, LeNet, AlexNet, ZFNet, GoogleNet and ResNet, CNN for detection, okay, and then CNN for semantic segmentation, just segmentation we have read, and then RNN, that is the recurrent neural network. So that is regarding the whole theory session. So any doubt in this? Anything you want to ask? The details I cannot cover in this 2-hour class. That is why details I have not discussed. But again, you can just check over the slides, and everything has been written over there. So you can just check over the slide after the class or anytime else. Okay. So I hope everything is clear. So by this I am just moving on to the question answer session. Which of the following statements are true for the pooling? It is common to use zero padding in pooling layers. It progressively reduces the spatial size. It operates over each activation map independently. It partitions the image into overlapping rectangles, taking maximum pool or average pool value from each of these sub-regions. So any guesses for this? So very easy, it is common to use zero padding in pooling layer. I have told you that we do not use this zero padding in the pooling layer. We use zero padding only in the convolution layer. So this is a first statement. And it progressively reduces the spatial size. This is very true statement, because that is what the main definition of pooling. We use pooling to reduce the spatial size of the activation layers. Okay, and then it operates over each activation map independently. Again, a true statement. Then it partitions the image into overlapping or maybe non-overlapping also. So anything rectangles taking the maximum pool or average pool value from each of this region. So B, C and D are the correct option. Option A is false. Zero padding, it is uncommon. It is uncommon in pooling layer. It is common only in convolution layer. Pooling layer, it is avoided because it just reduces the dimension. So that is why dimension or the value, okay, whatever value you will get in maximum pooling or average pooling, so it will affect it. So that is why we do not use this pooling in the we do not use this zero padding in the pooling layer. So this is regarding question number 1. So any doubt in this? Okay. Question number 2. Upconvolve the following input x using the filter h. What the value of 2,2 in the upconvolved feature map? We assume the index of the first cell array. So this is the input matrix, that is x00. That is nothing but this is a 2 cross 2 image matrix. Okay, x means nothing but your image, h means nothing but your filter. Okay, so x is your input image, h is your filter. So this x 0, 0, 0, 1, 1, 0, 1, 1 is nothing but a matrix, 2 cross 2 matrix. Okay. Similarly, this h 0, 0, 0, 1, 0, 2, 0, 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2. That means it is a 3 cross 3 filter. So it is a 2 cross 2 image and it is a 3 cross 3 filter. So tell me what will be the dimension of the output? Dimension of the output will be 2 plus it will be 2 it will be 2 what will be, that is 2 as we are doing the up convolution. So formula will also change. So let me just show you. So it will be 2 plus 3 minus 1. So that will be the output size. Okay, because here we are up convolving it. Okay, so we are not doing the down convolution or the down sampling, we are doing the up sampling. So this is the formula for your up sampling. Okay, So your output will be formulated like this: 2 plus 3 minus 1. 2 is the input size, 3 is the filter size, and minus you have to do 1, and this is the total filter size. So you have this input x 2 cross 2, that is this. So this is nothing but a matrix: 0 1 0 comma 0 0 comma 1, that is 2, and then 1 comma 0, that is 3, and that is 1 comma 1, that is 1. So this is nothing but your input, that is nothing but your input dimension. Okay, input dimension of your image. So this is input dimension of your image, and this is the filter that has been given in the question. Okay, h00, h01, h02, like this, that has been given in the question. So from that, first thing is to calculate the output size. As you are doing the up convolution, so this is how we calculate the output size. If we are doing the down convolution, then this would not be your output size. What will be your output size? That will be 2 minus 3 plus 1, right? That is how we calculate in the downsampling. But as this is an upsampling problem, so that is how we calculate the output size. 2 plus 3 minus 1 equals to 4. So 4 cross 4 will be your output size. Okay. So question it, what is the value at the output position 2 cross 2, 2 comma 2 0 base. So that is the question. So how you have to do it? You have to do it by this formula. So this is the formula of your up convolution that I have told, that I will discuss. So this is the formula. So your output PQ will be given by this, that is sigma I equals to 0 to 1, sigma j equals to 0 to 1, xij is nothing but your index of the image. Okay, xij is nothing but your index of the image, and then h p minus I q minus j. Okay, pq is nothing but your pq is nothing but your output dimension. So output dimension, we have this 4 comma 4 output dimension, and I is nothing but 2 cross 2 is our output dimension. Okay, so this is how we calculate the thing. So how we compute out the 2 cross 2 term? So very easy, we said p equals to 2 and q equals to 2, because our output that we have to calculate is 2 comma 2. So that is why we just set p equals to 2 and q equals to 2. For each input position, that is I comma j, find the corresponding filter index, that is uv we have to calculate. So uv is nothing but this index. Okay, so it has been tell as u, and this has been tell as v. So u is nothing but p minus I, v is nothing but q minus j. Okay, and add xij dot huv if uv that is 0 comma 1 comma 2. Okay, so that is the whole thing. So how we will calculate? First we will take the take x comma 0 comma 1, because x we have this 4 index. We have 0 comma 0, 0 comma 1, 1 comma 0, and 1 comma 1. So these are the 4 index we have. So for that we are just checking the first index, that is x 0 comma 0, then x 0 comma 1, x 1 comma 0, x 1 comma 1. That we will first check. So x 0 comma 0, our index of this I comma j is 0 comma 0, and p comma q, we already have pq as 2 comma 2, so p minus 0, q minus 0, that is p comma q will be equal to 2 comma 2 only. So we have to do h2 comma 2, and h2 comma 2 it has been already given, h2 comma 2. So h2 comma 2 0 1 2, 2 comma 2 is nothing but 0. So that is the thing. Okay, so let me clear the indexing. So this is 0 index, this is 1 index, this is 2 index, this is 0 index, this is 1 index, and this is 2 index. So 2 comma 2 means we are talking about this very element, h2 comma 2 means this very element, and for x also this is 0 1 and this is 0 comma 1. Okay, so 0 comma 0 means we are talking about this index. So whenever we are talking about h 0 comma 1, x 0 comma 0, so that is 1 into 0. So our answer will be nothing but 0. Similarly, we have to check for x 0 comma 1. So what is x 0 comma 1? X 0 comma 1 is 0 comma 1. That means this is x 0 comma 1. So this is x 0 comma 1, that is 2. So x 0 comma 1 we have. So just we will have this index 0 comma 1. And p is 2 comma 2, so 2 comma 1 should be our index. h2 comma 1 we have to find out. So what is h2 comma 1? 2 is this and comma 1. That means this row. That means our this will be our h2 comma 1. That is 1. So h2 comma 1 is 1 and x0 comma 1 is 2. So 2 into 1, that is 2. Okay, similarly we have to do for x1 comma 0. Again 1 comma 0 is 3. And what will be our 1 comma 0? 1 comma 0 if I take, so it will be 1 comma 2. Okay, so 1 comma 2, just see what will be h1 comma 2, h1 comma 2, so that will be 1. Okay, so 1 into 3, 1 into 3 is nothing but 3. Similarly x1 comma 1, x1 comma 1, again very easy, x1 comma 1 is 1, and then you have to do for h1 comma 1 also. Okay, h1 comma 1, that is very easy, h1 comma 1, h1 comma 1 is nothing but, yeah, this 2. So 2 into 1, that is 2. And then output, how you will calculate output? You have to just add over here. So output is nothing but 0 plus 2 plus 3 plus 2, that is 7. So 7 will be your answer that has been asked in the question. Okay, so that is shortcut how you have to do it. If you have to do the long cut, then what you have to do? You have to check for all the indexing, not 2 comma 2, but here as we will get 0, 1, 2, 3 index, so you have to check for all the index. For example, 0 comma 1 you have to check, 0 comma 2 you have to check, 0 comma 3 you have to check, all you have to check, and then you have to form the output matrix. Okay, so this is the total thing. So what I have told, any doubt what I have told? This is very important question and this can confuse you. So kindly ask me, no problem. Any where any doubt, you can kindly ask me. What I have told, I can again explain it from scratch. Yeah.
So please explain, sir,
Yeah.
another time.
Okay.
So how to form H also?
How to?
How to form the filter H T plus 3?
Filter is already given, right? So let me again show you. So this is the question. Sorry. Yeah, this is the question. This I have done in the long method, so this also you can check. This I have just given in short method and more explanation, so that is why I have kept over here and I have explained from this, because this is more easy to explain. So this the same thing, this I have done in long method, so you can just check it. So this is your question. Okay, so first just read the question. Upconvolve the following input x and filter h. Okay, what is the value at 2 comma 2 in the upconvolved feature map? So this is nothing but output. Okay, output of the up convolution. Okay, not down convolution but up convolution. And the one that we have seen in our theory, that is down convolution, but here we have to up convolve it. There is two things. One is down sampling that we generally do, and there is up sampling. For example, whenever you are given the max pooling layer, from max pooling layer you want to get the original image. Okay, so for that you have to do the original image or original activation map. So for that you have to do the up sampling. Okay, so that is why here this is a up sampling problem of up convolution. Okay, so here the input has been given, that is this is the input, that x0 comma 0 is given, x0 comma 1 is given, x1 comma 0 is given, and x1 comma 1 is given. That means input is given, and also the filter has been given. Filter has been given h0 comma 0, h0 comma 1, h0 comma 2, 1 comma 0, 1 comma 1, and similarly h2 comma 2 is given. So you are given a 2 cross 2 image, or sorry, not image, I should not tell image, 2 cross 2 input and 3 cross 3 filter. So what is the 2 cross 2 input? This is the 2 cross 2 input that I have written over here in short. Okay, so this is the 2 cross 2 input. Okay, this is I think 1, 1, 2, 3, 1. Okay, so this is the 2 cross 2 input. And what is the filter? Filter is 3 cross 3. That is also given us in the question. Okay, as 0 comma 0, 0 comma 1, 0 comma 2. So everything is given. So this is also given. So this is the filter. Okay, so this is the input is given, this is the filter is given. Now you have to up convolve the input. Okay, so is now the question is clear? At least the question is clear. Is the question here? Question is clear, right? Now our first thing is to calculate what is the dimension of your output. of your upconvolved output. So to calculate the dimension of your upconvolved output, this is how you have to calculate it. Okay, that is the input plus your filter minus 1. Okay, that is how you have to calculate it. So 2 plus 3 minus 1, that is nothing but 4. So your upconvolved output will be of the dimension 4 cross 4. So that you have to first calculate it. So any doubt what I have told you? It is not the downsampling. If we have this downsampling, then we have our formula, right? We have what our formula, that is input minus filter size divided by stride plus 1. That is how we do the dimension of the downsampling whenever we are talking about convolution. But this is not downsampling, this is upsampling. So that is the difference. So that is why output here has been calculated like this. That is input plus filter minus 1, that will give you the output dimension. So your output, upconvolved output, will be 4 cross 4. So now is it clear up to this? Clear, right? Okay, nice. So if this is clear, the rest of the things are very easy. Now what has been asked in the question? Asked in the question is what is the value at 2 cross 2 in the output or the upconvolved feature map. That has been given. So our feature map will be something of 4 cross 4 matrix, that we just understood it. Okay, so 4 cross 4 matrix, how it is indexed? It is indexed as 0 to 3. Now here everything has been indexed from 0. For example, how this image is indexed, not image again, sorry for that, input is indexed, that is 0, 1, 0, 1. Okay, 0, 1. So 2 cross 2 we indexed it 0, 1. 3 cross 3 or filter, how we index it? We index this 0, 1, 2, 1, 2, that is how we index. And if we are talking about 4 cross 4 output, how we will index it? We will index it as 0, 1, 2, 3. Okay, so this is also, I think, clear to you? Clear, right? How we will index this? 0, 1, 2, 3. Okay, that is how we will index this. Input we will index this at 2 cross 2 matrix, so that is why 0, 1. Filter, we have this 3 cross 3 matrix, so 0, 1, 2. This output or the upconvolved output that we will get, we just calculated it, it will be 4 cross 4, so that is why we will have 0, 1, 2, 3. Okay, so 0, 1, 2, 3, we have to calculate what will be the 2 at 2, comma 2, what will be the value. Okay, that we have to calculate it. Okay, so that how we will calculate it? We will calculate it very simple by this formula. Okay, this is the total formula. Okay, this is the total formula, but again I don't want to confuse you by this formula, but just understand this thing. Okay, so your output is nothing but that will be your this input into your filter, that will give you the output. That is very simple. And output you have to calculate at position 2, 2. This is nothing but indexing. That p, q is nothing but indexing. I, j is nothing but indexing. P minus a, q minus j is nothing but indexing. Okay, so you have to calculate at 2, 2. So that means p will be equal to 2 and q will also be equal to 2. Okay, so if p equals to 2 and q equals to 2, you have to just, what you have to do? You have to just multiply it, the xij into h p minus a, q minus j. So if ij, how many index we have? We have 0, 0, 0, 1, 1, 1, and 2, again 0, 0, 0, 1, 1, 0, and 1, 1. That are the 4 index we have for this ij or the input. And output, our index is already clear because we have been asked in the question 2, 2 we have to find. So p equals to 2, q equals to 2. So we have this I, j index, we have this p, q index. Now you can easily calculate the index of h. That I have termed it as u. U is nothing but p minus I, and v is nothing but q minus j. So if we know this, it is very easy. Just we have to do the calculation part. Very easy. So first we will talk about 0, 0 index. When the I equals to 0, j equals to 0, what will be u, v? P is 2, 2 minus 0, 2 minus 0 is 2, and q, 2 minus 0 is 2. So x 0, 0 into h 2, 2. So what is x0 comma 0? X0 comma 0 is, I think, 1. Yeah, 1 is right. So let me erase it. This is 1. So 0 comma 0 is, x0 comma 0 is 1. And what is h2 comma 2? h2 comma 2 is 0. So 0 into 1 into 0. 1 into 0 is nothing but 0. So that has been the contribution of your this index. Okay. Similarly, we have to check the contribution of 0 comma 1 index. So I equals to 0, j equals to 0, and just put over here. So 2 minus 0 and 2 minus 1. So we have to calculate for 2 comma 1. We have to calculate h2 comma 1. What is the value? So h2 comma 1, 2 is this and 1 is this. So 1 and 0 comma 1. 0 comma 1 is nothing but this. Okay, so that is 2. So 2 into 1. So 2 into 1 is 2. Similarly, we have to do calculation for x1 comma 0 index and 1 comma 1 index. And at last, as the sigma is here, so we have to just add all the contributions. So 0 plus 2 plus 2, 3 plus 2. So that is 5. 5 plus 2 is 7. So 7 will be your answer. Similarly, we have got answer for only this part. Similarly, you can calculate for all the parts. For example, when p comma q is 0 comma 0, so then also you can calculate what is the output. Then p comma q 0 comma 0, then p comma q 0 comma 1, then also you can calculate output. And if calculate all the output, you will get the upconvolved matrix. Okay, so this is the whole thing. So now is it clear? Clear, right? Each step I have explained, so I hope it is clear. Even now also, if it is not clear, I request you to please ask me, because it is very important. This is the most important or most confusing thing that you can encounter in this week. Okay, so any portion you have any doubt, you can please ask me what I have told. Any doubt, can please ask me. So your answer will be 7. Okay, again this is the simplified thing. This 2 slides are the simplified thing of your this 2 slide. Okay, this 2 slide I have just put everything at once, so that is why it can be confusing. That is why, to simplify things, I have given you this 2 slide. So this 2 slide you can easily understand how we can solve this. Okay, so this is the whole thing. Now let's move on to the next question. The softmax prediction of 4 different classes are this 0.1, 0.3, 0.2 and 0.4. Calculate the cross entropy loss for this sample. Use natural logarithm. If the true labels are 0, 0, 0, 1, round off the answer to 4 decimal places. So very easy. You have to just understand what, just remember what is the cross entropy loss formula. So what is the cross entropy loss formula? This is the cross entropy loss formula. I equals to 1 to c. That is nothing but all the classes. Okay, so all the classes means you have this first class, second, third and fourth. Okay, so it will be, in our question it will be I equals to 1 to 4, and then y1 into log p1, then similarly so your answer will be y1 into log p1, then y2 plus log p2, y3 plus log p3 and y4 plus log p4. Now very simple, y1, y2 and y3 all are 0. Then we do not require to even take the contribution of y1, y2 and y3, because all are 0. We can just take the contribution of y4, that is 1. y4 is nothing but 1 into log ln, or this log base e, ln means log base e. Okay, ln p4 is 0.4. So 1 into log of 0.4. So minus is also there, don't forget it. Minus 1 into log of p4. So that is the answer is coming 0.91629 something. So 0.9163 is your answer, rounded to 4 decimal places. So is it clear what I have told you? Just simple formula you have to understand. You have to keep in mind, that is L will be equal to minus of sigma I equals to 1 to c. All this is class. Okay, I equals to 1 to c, that is we have this 4 levels, right? So I equals to 1 to 4, then yi ln pi. So 1 to 4, 1 to 3, all the y contribution are 0. So 0 into something is 0 only. So that is why I have not even written it. So I can just write 1 into ln4. So that is what I have written, and minus sign is there. So by this just calculate it, and this will, you will get the answer. Okay, so very easy, I hope. Clear, right? Any doubt in this?
Sir, in assignment question, they asked average cross entropy, sir.
Average cross entropy.
Average cross entropy for two samples.
Okay, so two samples, I think for one sample, so average, you have to give average. You have to just calculate one by
Well,
one, and then you have to
calculate
give
this
average.
separately and
Yeah,
then
yeah,
take average.
yeah, yeah, yeah.
Okay, okay. Thank you, sir.
Question number 4. What is the main problem in stacking multiple layers to learn a large network with the limited data? Overfitting, high bias of the model, vanishing exploding gradient, possibility of data augmentation. So data augmentation is not a thing that is used in the training process. So option D should not be the answer, definitely. So it will be between this is data augmentation is nothing but we use the data augmentation to increase the data set. Okay, so that is why option D is always false. Yeah, overfitting, stacking multiple layers. So overfitting should not be problem. I think this high bias can be problem, and vanishing, mainly this vanishing or exploding gradient is your problem. Okay, this, that is the main problem, I guess. Yeah, vanishing and exploding gradient. So yeah, overfitting becomes the main problem if you have limited data. Okay, but still makes the network large. Many parameters are compared to training. So yeah, and then vanishing gradient, that is definitely a problem, become a training optimization problem when you stack many layers, especially without residual connection, batch norm, or careful initialization. Okay, so that is why residual connection is required. Residual connection is introduced in our ResNet model to just deal with all this vanishing and exploding gradient problem. We have this residual connection. Okay, so residual connection takes care, that is introduced in the ResNet, and that takes care of all this vanishing and exploding gradient problem. Okay, and high bias of the model, if I talk about B and D, that is high bias of the model. Deeper model usually have low biases. Okay, so yeah, so it can be taken as both way, like yeah, so yeah, okay, so high bias deeper model usually have low biases. That is true, they can fit the training data well. So this is not the main issue. Okay, that is true. Possibility of data, that is I have already told you, data augmentation, that's not a problem, it's actually a solution for limited data. So option D is always wrong. Option B, I can have doubt, like yeah, you can also tick it like high bias of the model. So high bias of the model, yeah, it can happen, because if you are losing information by your vanishing or exploding gradient. Okay, so no, but it is back propagation. Okay, so that is why it is, I think that is why it is wrong. So option A and option C is your correct answer over here. Okay, so this is the all theoretical question. So let's move into the next thing, that consider an input image of dimension this 19 into 15 into 3. That is your input dimension. It passes through a convolution layer with 64 kernels. Dimension 5 cross 5 cross 3. The image has been zero padded on both sides with 1 cross 1 padding, and convolved using a 2 cross 2 strand. So that is the total thing. Now based on the given data, solve the following question. So very easy. What is the dimension of the activation map? So that is the most important question I have told you. So dimension of activation map, I have told you how to calculate it. This is how we calculate it. Okay, here the symbol can be different, but just understand it. W output is W input minus KW. KW is nothing but filter size. Okay, plus 2p divided by s plus 1. Now what is p over here? P is nothing but 1. Okay, because 1 cross 1 padding has been given. Okay, p is 1, stride is 2. Stride is 2, yeah. P is 1 and stride is 2. So p is 1 and stride is 2. So keep p equals to 1, stride equals to 2, and KW has been given. What is the filter size? KW has been given, yeah, 5 cross 3 filter, right? So KW is 5. So similarly you can do for this H out also. So h out or the height of the activation map, that also you can calculate it. And d output is nothing but the number of kernel, that is given as 64, I think, right? Yeah, 64 kernel. So d output is very easy, that is 64. Okay. Now w output, that is w input. W input is 19 minus kw, that is 5. 19 minus 5 is 14. 14 plus 2. 14 plus 2 is 16. 16 divided by 2, so that is 8. Okay, 8 plus 1 you have to add, so 9. 9 will be your answer. So this will be answer. Okay, 9 into 7 into 64. Similarly, h output also you can calculate, and 7 will be you will get the answer 7. So this is your dimension of your activation map. Okay, so option C is the correct answer. So is it clear? Clear, right? Any doubt in this? Clear, right? This is I think very easy. Yeah. Now calculate the number of parameters in the convolution layer. So parameter, this is how you calculate the parameter, that is input number of channels into this dimension of your this filter into nk, that is the number of kernel of filter plus nk. So number of input of filter is nothing but 64. Okay, 64 is your nk. Okay, 64, and you have this 5 into 3, right? Yeah, 5 into 5. So 5 into 5, that will be your kh into kw, and c input is nothing but your 3. So just do it, and just do the calculation, and this portion will come at 4800, and plus you have to add this nk, that is 64. So answer will be coming 4864. Okay, again simple formula, and simple, just put the formula and get the answer. Okay, so this also I think it is clear to all of you. Clear, right? Okay, nice. Question number 7. Assume the convolution layer is followed by a max pool layer with kernel size 2 cross 2. Calculate the number of parameters in the pooling layer. So kernel size max pooling 2 cross 2 means stride will be 2. Okay. So okay. So here number of parameters has been, not the dimension, number of parameter has been asked. So number of parameter for a pooling layer is always equal to 0. So that again you have to keep in mind. If you are talking about number of parameter of the convolution layer, then you have to apply this formula. But number of parameters of a pooling layer, then it is very easy. But if you are talking about the dimension after the pooling layer, then what you have to do, you have to just divide it by 2. Okay, just divide it by 2, and you will get the divided by 2 or divided whatever the kernel size is, and you will get the output dimension after the pooling layer. Okay, so this is the thing. So any doubt in this, what I told? No doubt, right? So by this, let's discuss another problem. Consider a convolution layer with the input channel equal to 16. A kernel size 3 cross 3 is used to generate a feature map. Number of kernel used in this layer is 32. Calculate the number of parameters. So again, number of parameters is very easy. That is the same formula. Everything has been given. Input is given channel input. Yeah, channel input is given 16, and then kernel size 3 cross 3, that has been given. Nk, that is the number of kernel used, 32 is given. So just again do the calculation, just put it in the formula, do the calculation, and you will get the answer 4640. So this output dimension is very output dimension and parameter is very important question. So I hope this concept is clear to all of you. If this concept is clear, then definitely you can solve many questions regarding to your CNNs. Okay, so this is again a straightforward question, similar to your fifth question, I think fifth question. So it is very easy. Okay, and then let's move on to the
Sir,
yeah, please.
in assignment part they ask trainable parameter. Both are same, sir.
Yeah, parameters mean trainable parameter only.
Okay, including biases.
Yeah.
If it is excluding biases means any formula changes.
Yeah, nk will be there should not be nk. Okay, so let me show you. Sorry. Yeah, you can easily see this extra nk is for bias terms. Okay, extra nk plus this
Okay.
nk is bias term. If bias is not asked, you can just delete this. Okay, so this is how you
Okay.
have to
Okay.
solve it. Okay,
NK is bias term.
yeah, plus nk that we are doing, that is we are doing for bias. This is
Okay.
weights, this is bias.
What about previous term, sir? Multiply NK.
What is
Multiplied by NK, sir, in previous term.
this
C
is
again NK.
this is weights. Okay, this is weights. We you have two trainable parameter, weight and biases, right? This is weights, so weights should
Okay.
always be
Okay.
there.
Okay.
So that is why this nk will remain, but this nk is for bias, so you have to just
Okay.
delete it.
Okay.
Okay.
Thank you, sir.
Okay. Which of the following statement are true? Fast RCNN selects lesser number of reason proposal from a given image compared to RCNN. In fast RCNN, reason proposals are prepared from the convolution features of a given image. RCNN computes CNN feature on the whole input image. Reason proposal network RPN is trained to produce reason proposal directly from the last convolution layer. Okay, so this fast RCNN select lesser number of reason proposals from a given image compared to RCNN. This is absolutely false. So fast RCNN does not reduce the number of proposal. Both typically uses the selective search, so that is why it does not reduce the number of reason proposal, but it reduces the time, not the number of reason proposal. Okay, so that is why this is false. Fast RCNN reason proposals are prepared from the convolution feature of a given image. So in fast RCNN, reason proposals still come from the selective search, not RPN. RPN, it comes from RPN in this faster RCNN. Okay, so that is why this is also false. RCNN computes CNN features of the whole input image, so that is also false. RCNN CNN applied each reason proposal separately, not the entire image. Entire image is for fast RCNN. Okay, not for your RCNN. So this is also false. Reason proposal RPN is used in this faster RCNN. That is true. So again is a pure theoretical question. So I request you to please go through all the theory for this detection as well as Unet. Okay. Please read what is RCNN, what is this fast RCNN, faster RCNN, and also Unet. Everything I have given in this slide, so you can just read it, and by reading it only, many of your doubts will get clarified. Okay, so this is again a proper theoretical question. So option D is the correct answer. Now last, in an object detection problem, the time taken to generate all proposal is 0.75. Okay, there are 4 number of proposal generated. Okay, what is the inference time of the faster RCNN? Okay, if the convolution time and the time taken by the fully connected layers are 2.25 and 1.75 respectively, round of the answer to 2 decimal place. So for that, convolution time has been given, that is 2.25. Number of proposal, that is 4, and this is the FC time. Okay, that is fully connected layer time, that is has been also given, that is 1.75. Okay, so you can easily solve this. Yeah, you can easily solve it. So convolution, yeah, so convolution time and the time taken for fully so convolution time is this, that is 2.25, and fully connected layer time, that is 1.75. So what is your formula? This is your formula for your inference time in case of this faster RCNN. Okay, in case of this reason based RCNN, here the reason number of reason proposal is also multiplied. Okay, so if it is only RCNN problem and not a fast RCNN or faster RCNN, then you have to multiply the number of proposal over here also, that is 4 into convolution time also you have to do it. But as it is a faster RCNN, it is 1 into convolution time always. So convolution time, it is 2.25. So this is already clear, and then number of proposal is 4 into FC time is 1.75. So total it is 9.25 is your answer. Okay. So again it is a total formula based question. So just put the formula and get the answer. Just remember, if it is just RCNN, then you have to multiply proposal number of proposal in your convolution time also. Okay, that you have to keep in mind. Okay, so this is regarding the entire session. So any doubt in any questions? Okay, no problem. So
Sir,
yeah, please.
sir, in assignment part, two different questions are there. They asked incorrect softmax probability and another one is corrected softmax probability. Any specific formula is there?
Okay, I will solve and give after your this answers are released. I can solve and put in that document folder. Okay, then you can check it.
Okay, okay. Thank you, sir.
Okay,
Sir, I
and
have another doubt in last week's session, sir.
last week assignment.
Last week, your discussion class
Okay,
on formula.
okay. So which formula?
Question number six. Question number six for the calculation of scatter matrix within class.
In the question answer section or where?
Yes, sir. Question number six.
Yeah. Okay. Okay.
Uh,
Yeah.
sir, third one, class covariance matrices.
Class
Third part.
variance matrix.
Form
Yeah. Yeah.
class covariance.
Yeah.
Sir,
Yeah.
you put the formula is sigma 1 equal to 1 by 4 S1.
Yeah. Yeah.
And also you calculated the SW is sigma 1 plus sigma 2. It's correct, sir?
Sigma 1 plus. Yeah. Yeah. Yeah.
Is it correct?
Yeah, yeah, that is how you have to calculate according to me.
But SW equal to S1 plus S2.
SW equals
But
to
you put
no, no, no. You have to
yes.
calculate this first. Okay, so that is 1/4 or 1/5. Again, that can be a confusion. It should be 1/4 or 1/5. Generally, two things are there. One is population and one is sample. Whenever there is population, then you can just how many data samples are there. You can do 1/5 if it is a population, but normally all the problems are for sample. That is why we do the 1 by n minus 1. So that is why you have to do this 1 by 4, 1 by n minus 1 and 1 by n minus
Okay,
1.
okay, okay. But another one scholar problem solving session, she told SW equal to S1 plus S2.
Okay, so I don't know.
So this
According
is
to
the
me,
confusion.
option A is coming 3.3 minus point 0.3 minus 0.3 5 comma 5. Yeah, so I think answer is also coming, right? Option A is also coming. So I
Yes,
think
yes, yes,
this is
yes.
how you have to solve it. Okay.
But assignment part, SW equal to for SW equal to S1 plus S2, the answer is coming.
Okay, so that is a problem. Okay, so if
There is a confusion, sir.
okay, okay. So according to me, you have to do this. Okay. If
Okay,
in
okay,
your
okay.
assignment it is coming like that, then I cannot do anything. But according to me, you have to do like this. Okay.
Okay, okay, okay.
So this
Thank you
was
so
yeah.
much.
So I just want to end the session with some of the quotes. So yeah, so whatever we have discussed regarding this fast RCNN or RCNN, these are a two-stage detection. Okay, so we have moved from two-stage detection to single-stage detection, and YOLO or you only look once is one of the most famous model that has been used in many research. You can just open the Google Scholar and you can get many research regarding YOLO. Okay, they're different. So this YOLO code I have given you, so you can just check how we this is the result. Okay, so this is YOLO model. Again, we are just taking this model. This pre-trained model are available. Just we can take the model, and we can if the classes that we require, that is same as the pre-trained model, then we can just directly take the model and we can do the inference. Okay, so this is, you can just see that is how we have done the inferencing. Okay, so this is the I think, yeah, this is the dog image, this is the image, this is the image, and this is the results. Okay, so dog that has been detected and person that has also been detected. So that is without any training. Okay, without any custom training. But also what you can do, you can just do the custom training. Every methods are there. So RoboFlow universe, every method are there. So then what has been done in this code, the data set has been developed for this I think, yeah, football players, etc. Okay, so then this data set has been used for this custom training. Okay, so we already have this pre-trained model that I have already told you, but now we have to apply this transfer learning. So whenever we are applying this transfer learning, what we are doing, we are taking a pre-trained weight, whatever the weight is there, and then we are from our own data set. This is the data set that has been shown in all this. So this is the data set. That data set we are taking. This is the football player object detection data set. So that we are taking it, and then we are doing the custom training. So this is the custom training. Okay, so then you can do the custom training, and then you can now after doing the custom training, so earlier there is no pre-trained class. Okay, there is no player class. So if you are doing the detection with just the pre-trained weight, so you cannot get the player class. But after your custom training, just do the custom training, now you can get all the player detection. Okay, so that is the player, referee, etc. detections. Okay, so that is known as this transfer learning process. Okay, so this is very popular model, YOLO. So I request you to please see this code. This will be very useful. Also for those who are very interested in research purpose, so this code that I have also included many things, so just read it, whatever I have included, and you can do the custom training. Anything you can do the custom training. Okay, so if you have a data set of your own, annotated data set, because this is a supervised learning, so you have to, what you have to do, what is the process? First you have to collect the data set, then you have to annotate it by your own, and then you have to you have to supply this data set to this pre-trained model to do the transfer learning process to get a custom training model. Once you got the custom training model, you can do the detection on your unknown data set. Okay, so this is the whole thing. I will please request you to please see this code, that is very important. And the code I want to see, that is the very popular vision language model that has been used, like RNN, etc. we have discussed. So what are the applications? So application I have told you, like image captioning, video captioning, etc. So this Florence 2, that is a model that has been given us by Microsoft. So this is one of the most important models. So by this we can get many type of things. Okay, every theory I have given here, so you can just read it. So by this, let me see it. Yeah, so by this we can get many type of detection. For example, this object detection also we can do. Just write it like whatever the things that we want, and we can do the object level detection also. Okay, so here it has been told like object detection, so all the detection that has been given, like man, sunglass, everything, it will get detected. Okay, then we can do another things also, like captioning we can do, detail captioning we can do. This is, I think, detail captioning. So detail captioning, for example, detail captioning means this captioning has been generated. Okay, so that is detail captioning. Open vocabulary detection also we can do. For example, the what we want to detect. For example, we only want to detect this finger image, so just supply this text, and by this we can get the finger image detection. And then we have this dense region captioning, that also you can do dense region captioning. Dense region captioning means only captioning means captioning means that whole sentence, right? This detailed captioning means this whole sentence, but here this dense region captioning means you can get the dense captioning. Okay, like man with the beagle dog in the outdoor cafe. So see how much detailed captioning has been generated. So that also you can do. You can do the OCR, that is optical character recognition, very important. For example, you are supplying any document and you want it to read it. For example, this by this board 34T655 written in this number board of the car, and you can see how it has captioned this. So this is known as OCR, or this optical character recognition. Okay, so that is very useful whenever you are supplying any document and you want to read it. So that is very important. Also, yeah, handwritten text is there. So OCR with reason. So each reason it will do your OCR. Okay, so that you can also do. Similarly, there are other tasks. Yeah, referring expressing segmentation. For example, whatever man has been segmented, so the whole man has been segmented. So that also you can do. So this is very useful and interesting model. So I again request you to kindly see this code, and again you can just play with this code whatever you require. You can supply your own image. So just see wherever the image has been supplied, where the image has been supplied. Let me see. Yeah, this is the data that we have loaded it, and each I think, yeah, each, this is the model we have done it, and yeah, this is the image supplied. So you can just load your own image, you can put your own image, and you can just play with the model. Okay, so this Florence 2 that has been released by Microsoft, this is one of the most important vision language model. Okay, so this is another application of whatever we have learned from our theory part. So by this I am ending the session for today. I hope it is useful. We will meet on the next this Friday. I will take one extra session to end this course from my side. Okay, so that is all from my side. So bye everyone.